only need 1 hour to tell you about sustainability. I'm going to do sustainability today, and then we'll, on Wednesday, tackle more theory. Okay? And actually finish off that deflection problem. I think we have time. Okay, sustainability. Have you had lectures in other subjects about it? No. Okay. Monash is big on sustainability. Sustainability is very important because we're ruining the world. So, are you all aware you have access to a Moodle site? The first year sustainability site on Moodle? When you go into Moodle, you'll see it there. In the project, the final project, there is a small section, Task 3, which relates to sustainability. As you can imagine, this subject is a theoretical subject. So in terms of how we can link your footbridge to sustainability would be a bit tenuous. We would have to spend a bit more time on it. So in the project, Task 5, unrelated to your bridge design, you are to go around the campus, if you haven't read the brief yet, and you are to find 5 examples of where you can improve the sustainability or the environmental aspect of a structure, of a building, by retrofitting, by doing something in terms of water tanks or shading or solar panels or something like that. So now I'm just going to introduce you to sustainability. I'm not sure if you've met this definition before, but the most commonly cited definition of sustainability is that sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. And that definition came about in 1987. There are various, it's quite a good first year sustainability site, so if you're interested, even if you're not interested, go and have a look and play around and have a look at what's there. So when we think of sustainability, usually we just think of the environmental side of it, but there really are 3 aspects to it. Oh, wow, I've lost you already. Bye. Okay. There are 3 aspects to sustainability that need to be considered: the environmental, the social and the economic aspects. So we know how we have to look after our world and the non-renewable resources we are currently using up, but we know that unless there's an economic incentive to do so, we're very hard pushed to do so. And as well as that, socially, well, we're not willing to do away without our air conditions or do away without our cars and use public transport. So socially, we have to be able to do that, all those environmental things. So one way of looking at it is to have these 3 Venn diagrams, and the part in the middle is considered to be the sustainable part. Another way of looking at sustainability, an alternative, more modern, fresh approach, is to consider the 3 elements where the outside circle is the physical environment. So in this case here, it's the physical environment that drives everything, as a healthy physical environment is required to produce a continually vibrant social and economic environment. So if it's good for the environment, if we like doing it, and finally, sometimes we'll do something even if it is not cost effective. But if it is cost effective, that of course is the best sustainable structure. Well, that's the sustainable thing that will be taken on board quickly because it's cost effective, it's socially it's good, and it's good for the environment. So we all know, I think, of all these sustainability problems: climate change, energy use, soil erosion, reducing air quality. We all hear stories about smog in other countries, and we don't want that happening here. Ozone depletion, we know about that here with us getting sunburned. Using our resources, natural resources, and reducing water quality. So all of these problems involve engineers. And there isn't, how many of you are doing environmental engineering? Yeah? Good. So you've probably heard all of this before, but here's my slant on it. And water quality, soil erosion, air quality, if we lose those aspects, we are going to lose our biological diversity, which we do require for the natural processes which produce good quality water, soil and air. So examples of unsustainable systems I think we all know. How many of you drove here today? Yes, we're very bad. Why don't they just put a train here? But anyway, we use our public transport. Most of us probably could have got here by bus or some other means. We are also reliant in Victoria, especially on fossil fuel use, which I'm not happy about. How many of you have solar panels on your homes? Good. Okay, and how many of you go to a lot of effort to put the right thing in the right bin here when it comes to recycling? Excellent. So we're slowly getting there. I'll skip that one. I today am not going to look at that general thing. I'm going to look at how we can have an impact very quickly, not so even in this course, but just the way you want to live in your homes, and that's through passive design. Because in buildings, passive design is a major key to sustainable building. So what is passive design? Oops. Passive design uses free, renewable sources of energy, i.e. the sun and the wind, to provide heating, cooling, ventilation and lighting, thus reducing and in some cases removing altogether the need for mechanical sources of heating and cooling. Passive design basically is the way they used to live in the old days, where they didn't have the option of turning the aircon on, so they thought much better about their designs. And we have come away from that now by using artificial means of heating and shading, and we've come away from actually doing the easy things to make our buildings sustainable. So we need to go back and look at the easy way to make buildings sustainable passively. So engineers, as part of design, we need to consider many sustainability issues, such as reducing our resource use, reducing our energy use, reducing waste produced, improving profitability and competitiveness, and improving human use or comfort. So today, in today's brief intro, I'm going to be looking at passive design, which looks primarily at reducing energy use and improving human comfort. And in some structures, passive design can make a great contribution to the sustainability of a structure. So here you have a typical example of a house that has awnings where awnings are required, and windows where windows are required to allow sunlight in where we want sunlight in, and to allow heat to escape when we do want heat to escape. So passive design, as well as being energy efficient, can also reduce temperature fluctuations, improve indoor air quality, and make buildings more comfortable to live in. And at the end, I'll show you a video of the council house that's in the city that has a 5-star rating. So passive design impacts on three principal aspects, so three principles of sustainability. We've been through this: the economic, the environmental, and the social. So it's a good way of covering it all. Most of the following material has been sourced just from a technical manual. As I said, this is just designed for lifestyle. This is open to the general public. You can have a look at. So by all means, have a look at this website here. Okay, so we want to reduce our household energy use, so we need to be aware of what how our household energy use is spread. So over here on the right-hand side here, what I've highlighted in this pale, horrible apricot colour is the fact that heating and cooling, on average, make up 38% of our energy use. So other things here, the other colours aren't in colour, unfortunately. So this is water heating. We know how to reduce that, either turning the temperature a little bit down on your control switch, very simply. You can all do that tonight. Or putting solar panels, putting panels on the roof. Okay, other appliances in here, then we have lighting, cooking and standby. But heating and cooling make up a major component of our energy use. When you actually look at that in terms of greenhouse gas emissions, that component actually does reduce down to 20%. And the difference between the home energy use percentage and the greenhouse gas emission percentage is the fact that a lot of heating in households, well, here in Victoria, use gas, and natural gas has approximately 1/3 of the CO2 emissions compared to electricity. Okay? So we want to try and reduce that percentage down. So the fundamental principles of passive design are simple and can be applied to various climates and building types, but you have to apply them correctly. So consideration of the following aspects is vital. A lot of this is obvious. You're sitting there going, obvious, obvious, obvious. Yes, it is obvious, so therefore we should be doing more of it. So we need to make people aware of it so we can implement it. When you go see a designer or an architect and they come up with a wonderful design, you may say to them, is my son coming in the winter? Have you designed it so my son is entering my house in the winter but not in the summer? Have you sat my building on the site the right way? I don't care if it doesn't face the road. So just as the general public, you should be aware of these things. So let's look first at orientation and sun control. So in hot climates with no winter heating requirements, so up north, orientation should aim to exclude the sun all the time and to maximise exposure to cool breezes. I don't know how many of you have been up to Queensland. They have a lot more fans there and a lot more louvers on their windows for their natural ventilation compared to Melbourne. In other climates, such as down here, we need a combination of passive solar heating and passive cooling. The optimum degree of solar access and the need to capture cooling breezes will vary depending on the climate. So up here, up north, where it's hot all the time, there's also high humidity. So the construction up there is typically lightweight construction. It's timber construction. They use ceiling fans, they site the building to expose it to breezes, and they shade all year round. So they may have evergreen trees around their houses that shade all the time. Down south in Hobart, even in Melbourne, we have low humidity. We have 4 distinct seasons. I'm losing some more.
So you study for the quiz.
Oh, for the test. You should have studied already. It's all right, I won't cry. Okay, down here it's a bit late to study, isn't it? No, it's never too late to study. Down in Tasmania, in Melbourne, we have 4 distinct seasons we have to deal with. It's freezing cold at the moment, but it gets boiling hot as well. So we need to maximise our north-facing walls by using shading and adjustable shading. We need to draw... Oh, come on, everyone. Can you just don't be rude? If you're going to get up, go now. Okay. The doors are locked. No one else is allowed to leave. Okay. It's a fire. We'll all die together. So I can't be held responsible because I've died with you, as long as I don't abandon the ship and run out in the last minute. Then I'll be in trouble. Okay, down south here, okay, we need to shade in the summertime, but allow the sun to come in the winter time. So it's very important. I think you all know which way does the sun, where does the sun rise? Rises in the east, travels through the north and sets in the west. In the summer it's a lot higher in the sky. As I said, this is obvious. In winter it's a lot lower. But making use of the fact that we understand the difference in the angle. Here we have Sydney. I couldn't find one for Melbourne. At the winter solstice, at the lowest point, the sun never gets up higher than 33 degrees in Sydney. In the summer, the sun angle is as high as 79 degrees. So we need to be aware of that difference in the sun angles. Here we've got Melbourne. Melbourne is very similar to Sydney. So the other thing to be aware of is, of course, see on the south side of the house here, shaded in blue. The south side of the house, irrespective of whether it's summer or winter, is always in shade. So normally you don't put your living area on the south side of the house. That's where you would put your laundry and your bathroom, where you don't care about the fact that the sun isn't shining into the rooms. So you put your utility rooms usually on the south side and your living kitchen areas on the north side, so you can make use of the sunlight. Cheers you up, doesn't it? Sunlight. Okay, so shading reduces summer's temperatures, thereby improving human comfort and, of course, saving energy. Direct sun can generate the same heat as a single bar radiator over each square metre of a surface. So providing that shading to a window to keep the sun out can have a significant effect on how cool and hot your building is in. If anyone wants to have lunch on the, what's that building on the loop with the big glass foyer? I forgot what it's got. Really boiling hot, terrible design. The Strip. Has anyone had lunch in the Strip? Yeah, well, in the winter time, it would be wonderful to go have lunch in there today on a sunny day because it would be toasty and warm. But in summertime, it's stinking hot in there. That's a shocking energy design building. Anyway, have a look here. In the summertime, in some place like Melbourne, you wouldn't put an evergreen tree next to a house. You would put a deciduous tree. So in the summer, you have shading, natural shading, and in the winter time, you can allow your sun to come in. Now, because the sun is lower down in the sky, it will reach further in. So you can also, if you don't want to have trees, have louvers, which are very trendy nowadays, where you can actually block out the summer sun. However, when you open your louvers, you can get a lot of sun coming into your building. So on the north part of the house, because of where the sun is in the sky, what you need to do is you need to have horizontal shading. So an awning is enough to keep the sun out. However, in the east and west part of the house, your building, where the sun is rising and setting, it's important to have vertical screening. So you need to have shades that will cover up your window altogether. Has anyone got their bedroom on the east or the west, or their television room, and the sun comes shining in on you and you can't see anything and you've got to close your Venetian blinds? So on the north side, horizontal shading is good enough. On the east and west side, you need vertical or adjustable shading. So here is who needs a computer package. Here in this one A4 page, we can work out what sort of awning, how far out to make our awning in order to keep out summer sun but let in some winter sun. So you can see here, because of that difference in the sun angle, you want to put awnings on houses so you can keep out all your summer sun but let your winter sun into your building. So in this graph here, what we're looking at is these are all different places in Australia. This here is the coefficient C, which, if you have a look here, is the ratio of your horizontal awning to your window height H. So C here is equal to E on H. So depending on where you are in the world, Darwin is a lot higher up. Okay? If it's closer to the equator, the sun is higher up in the sky. The further you are from the equator, the lower the sun is in the sky. So it's very important you realise where you are in the world as well as to how big an awning you require. But in this case here, we've got Melbourne here. I've dashed it in this blue line here. This, what we're looking up here, this ellipse shape here, basically relates to what amount of sun you want to block out. So if I said, I want to block out all of this sun from my building. So from the 17th of October through to the 24th of February. So through my warm months, I would come down this diagonal line here, and there where it intercepts, you can see here, my blue line, that is a value of, I'll just call it 0.5 to make my maths easy. So that's my value of C. So if my window is 1 metre high, I would require an awning overhang here of 0.5 metres. So that's a very simple way of actually telling you how far out your awning needs to be. If, however, I said I don't want my awning coming out that far, or I don't want my sun blocked out in October because it's still quite cool in October, then you may decide, okay, I only therefore want the worst month. I only want to block out that region in there. So from November, December through to mid of January. You would then come down this line here, and you can see here your C coefficient here is of the order of 0.3. So therefore you would only need an awning 0.3 metres in order to block out all your summer sun but allow your winter sun into the building. So very simple. There'll probably be lots of computer packages you can use to tell you. So if you drive past those new houses, and we won't name any names, like I do, those ugly box houses, especially those, what are those French ones? Why would you want a French provincial house in Melbourne? I don't know. And they don't have any awnings at all. You should be shaking your heads going, God, they haven't even bothered to put any awning on. So for them, that's cost cutting. For you, it's not, because it's a higher energy bill. So we need to go back to putting, or you look at all the old houses, all the Victorian houses, they have verandas on them. They all have eaves on their houses. They have awnings over their windows. Because in those days, you didn't have artificial means of heating and cooling. Well, heating you did, not cooling. So you would pull all the blinds down to keep your house hot. Cool. Okay, that's the summer. Now, awnings do not have to be boring. Okay? Here we have the Milwaukee Art Museum, designed by Santiago Calatrava, who is a Spanish, he calls himself, well, he is an architect, a sculptor, and a structural engineer, so a man of many talents. And he designed the new entry foyer for the Milwaukee Art Museum, which is over 100 years old. So his brief was, have I got his brief in here? Here is his brief. The brief he was given stipulated a grand entrance, a point of orientation for visitors, and a redefinition of the museum's identity through the creation of a strong image. This foyer, this is what you call a brise soleil. It's sun shading, French for sun shading, basically. It actually is a kinetic structure. It actually opens up and closes. So here you can see with the awnings closed, and at 10 o'clock every morning when the museum opens, this thing opens up. He actually is known for his flowing curved buildings with designs suggesting stylised natural objects such as wings and waves and skeletons. And I think this is an absolutely gorgeous structure. And I think I have, over here, I've put a video. Hang on. All displays. Not that one. Let's go back. You've got to see it opening. You've got to see it opening. Because this is such a cool structure. So don't think awnings have to be boring. So this has a wingspan of a Boeing 747 jet. It has ultrasonic wind sensors that automatically close if the wind speed is higher than 37 kilometres per hour. How cool is that? That's worth going to Milwaukee. Excuse the music. So it is opening up a little bit faster, you can tell from the people. But so that's why I don't want you to think that sustainability is all about boring, because it's not. It so is not. You can do wonderful things with it. Okay, another 11 seconds, 10 seconds. Okay. So that's the brise soleil. Do you love my French? Foyer. Okay, let's go back. Okay, another interesting structure. Oh no, I won't. I'll do that a bit further along. Okay, the next thing I want to look at, as well as shading, which is a very easy way to cool a building down, is thermal mass. So thermal mass is the ability of a material to absorb and re-radiate heat energy. What am I talking about? You've all walked past a tall brick fence on a hot day and put your hand up against it and felt the heat in it. You all done that? No, do it on a hot day and you can feel the heat coming out of the brick wall later in the day. So that is the thermal mass. So thermal mass can help with both heating and cooling. So do we want brick Would you want to have a brick building up north in Queensland with the heat shining on it all day and heating up the building? No. Does anyone live in a triple brick house that is fantastic for 1 day, 2 day, but once it heats up, it never takes ages to cool down? Yes. So in winter, we want to allow our thermal mass to absorb the heat, but we're not talking so much about the external walls, we're talking about the flooring. So if the winter sun shines into the building and you have a concrete slab on the ground, or you have tiles on the ground that can absorb the heat, or you have a solid brick wall inside the building, that absorbs the heat during the day, and then in the evening it re-radiates the heat back into the building, so it doesn't get as cool in the evening. So in the summer, we want to protect our thermal mass from direct sun, so we put our shading on, or we have our awnings in place. And if the building does heat up, it's then important we have our natural ventilation to purge the building in the evening. So the thermal mass when connected to the ground, so slab on ground is actually an environmental design, a good sustainable design, not so much in terms of the concrete, but in terms of the fact that when connected to the ground, it also acts as a heat sink. So it can absorb the heat, and actually if the ground under is cooler, it can actually pull it out of a building. So high thermal mass materials such as bricks and concretes absorb a lot of energy. Lightweight materials such as timber have low thermal mass, so they don't absorb as much heat into the building. Water actually has the greatest thermal mass. So how about making walls from water-filled containers? Have a think about it. Okay? Thermal mass is no substitute for insulation, so I'm not talking about insulating the building. Shh. Thermal mass stores and re-radiates heat, while insulation stops heat flow into and out of a building. So the best way to design a building, if you want to have brick wall, is to actually have the brick wall on the inside of the building. So on the outside, you have your insulation, you have your cladding, and it doesn't absorb the heat during the day. But on the inside, if you have your heaters on and your occupants in there, the building is warm, the internal walls, brick walls, absorb that heat and then re-radiate it out at night. So thermal mass should be left internally exposed. Also, finally, it shouldn't be covered in carpet. If you cover a concrete slab with the carpet, you're losing the effect of the thermal mass. Okay, thermal mass is most beneficial when there is a big difference between day and night or diurnal outdoor temperatures. So here in red is the outside temperature, and we know that overnight it cools down. So here we have the morning time here. It's nice and cool in the morning, then the sun comes up and the heat starts to rise. So in your building, if you have a double brick solid house, it actually doesn't heat up as the day heats up. It will stay cool. So there's a huge difference between the inside and the outside of the buildings when the inside of the building heats up. I have a timber Victorian house, and my house will heat up by the end of the day on a hot day. So what you need to do is you have this lag in the heating of your house and in the temperature outside. So if you're aware of that lag and you close windows when your outside temperature starts getting hotter than the inside, and then in the evening you open the windows again, okay, that's a very efficient way of keeping your house cooler. So high thermal mass buildings, because of the time lag between the internal and outside temperatures, benefit from night purge ventilation. So opening windows at night and letting the cool air come in is a great way to keep your building cooler. So we've talked about thermal mass, and ventilation goes hand in hand with thermal mass. So we want cool breezes. So sometimes we open our front and back door, we have no cool breezes. So it's important, of course, that you have these openings in line with the way the wind blows in your town, in Melbourne. Okay, so you can't just have windows open the wrong way around. You need to have them aligned with the prevailing breeze. So that's why you see in Queensland they have a lot of louvers to allow that night purging of the building, or day purging to keep it cool. So maximising the flow of cooling breezes through a home is an essential component of passive design. But thermal chimneys is taking it one step further. Thermal chimneys is where you have components of a building, an atrium space, where you can actually open up the space high up, open up a window or a louver high up. So thermal chimneys utilise convective currents to draw, they actually draw the air out of a building. So convective air movement relies on hot air rising and exiting at the highest point. And if air is rising and exiting, it's being pulled in. It's being drawn in somewhere else in the building. So you draw the cool air in from shaded and external areas. That's a good reason to have a purge pool. Like I said, sustainable, doesn't have to be boring. Have yourself a nice pool next to your house. Have it so when you get the prevailing winds coming in, the water actually flowing over your pool is cool. The air flowing over your pool cools down, evaporative cooling, and enters your house and keeps your house cool. So siting a pool in the right spot will actually help keep your house cooler. Now, all these things, a lot of them are taken from nature. Okay, a lot of these things have been done for hundreds of years. Have you all heard of biomimicry? That's where you imitate life. Well, this biomimicry is Greek for bios meaning life and nemesis meaning imitation. So, imitating life. So thermal chimneys, this case over here, okay, we didn't invent it. Thermal chimneys are inspired by self-cooling mounds of these termites. I won't say microtermus, Michael-Sensei termites. Have you all seen these termite mounds? You must have seen them over the years. Okay, temperatures inside these nests lie within 31 plus or minus 1 degree, whether it is winter or whether it is summer. Outside, the temperatures can vary between 3 and 42, but inside, the temperatures never vary more than 1 degrees. So if you look closely at these thermal mounds, they have actually all these channels created. At the top, the hot air is pulled out, and the cooler air lower down comes into the chimney, into the mound to keep it cooler. I'm going to show you a video shortly of the Council House 2 building, and that also works on a thermal chimney where the air at night is drawn out and purged. And cool air, all the windows are open, also the cool air can be pulled in. One type of termite, the magnetic termites, get their name because they build their large wedge-shaped mounds with the long side aligned north-south. So they actually align it that way, north-south, so they get less sun shining on their north side to heat them up during the day. So they've learnt which way to actually site their mounds to minimise heating up and cooling down. Now these termite mounds are amazing. If we compare the height of an average termite nest with the size of a working termite and adjust the scale to a human being, the termite construction would be like a 960 metre high skyscraper, which is higher than every building in the world. So it's 5 times higher than the pyramids. And if we consider that termite finishes its structure in 3 to 4 years, that's equivalent to many thousands of human years. So termites are amazing. We didn't come up with these designs. We looked at nature to help us improve. Here's another building. Has anyone been to Paris? Okay, this is the Arab World Institute, Paris. I saw it when I was there many years ago. Does that look like an old or a new building to you? It looks modern, doesn't it? So this building was inspired, so it is the Arab World Institute. It was inspired by the Islamic architecture, so these patterns here. The building facade utilises 30,000 photosensitive apertures that open and close to modulate the light and the heat that enters the building, mimicking a human eye. We all know that our eyes get bigger or smaller, the eyeballs, depending on whether you're outside or inside. So if you sit there on a sunny day when it gets shady and sunny again, you'll see this facade moving and opening up. The apertures open up and they close. So here they are in an open position, and it's got fantastic shading into the building here. Now I covered this up because I'm always amazed at how old this building actually is. It looks relatively new. In the first lecture I showed you the RMIT hub in the city and said, wow, look at this, isn't this wonderful? To me this building here is just as good, and this was completed in 1987. So this is almost 30 years old. So again, this is borrowing from nature, the eye, to build a very a sustainable environmental building. Now all those things are just putting practical common sense to use. A more high-tech way of trying to be sustainable is looking at phase change materials. So phase change materials absorb and release energy by melting and solidifying within a temperature range of human comfort. So within a couple of degrees, they heat up and they cool down. So when the temperature rises over a certain value, say 21 degrees, the material will absorb the excessive heat by energy by melting. So we all know when we have an ice block on us, that will absorb the heat around us, make us feel cooler, and it will melt. But these phase change materials change phases, okay, in a much smaller temperature range. So when the temperature falls under a certain value, maybe 15 degrees, maybe 10 degrees, the material then releases this stored energy again by solidifying. So these phase change materials are slowly being integrated into plasterboards. So they have these little capsules here you can see on this side. Within the plasterboard, they have these phase change wax-type microcapsules in their structure. The thermal capacity of a 13mm thick plaster layer with 30% microcapsule content is claimed to be equivalent to that of a 6-inch brick wall. So these things are around, they are on the market, but of course the cost is prohibitive. So they're still expensive. So we haven't got that economic part quite sorted out yet. We are now going to show you a short video of the Council House 2. Has anyone been in there? It is on Little Collins Street in Melbourne. Every year when Melbourne has its open house day. Have you been to any of those? Yeah, a weekend in. This building is usually open. It is the first accredited, I called it 5-star. It's actually a 6-star building built in 2006. You'll see here there's a timber facade there. That is, of course, awnings that open and close to provide natural shading. The cost of the building was $55 million. When they built this, they said, we are going to build, as a city of Melbourne, we owe it to the people to build a highly energy efficient building. So of that $55 million, $11 million was spent on green design features. So quite a lot of money. So in terms of energy usage, it uses 80% less energy than a conventional building and 70% less water. And that equates to a 300 to 400 annual saving in energy costs. So hopefully some of you are sitting there going, 300,000, so into $1 million, that's 11 million, that would take 33 years to pay off. So there's not really an economic case there to put forth. 33 years is too long a return period. You all agree with me? They built this anyway, and they discovered that they saved $2.4 million annually in reduced sick leave due to the healthy environment of the building, and that was a total surprise to them. So by not having a closed building with air conditioning and heating, by allowing clean air in every night to purge the air, people weren't getting colds, people weren't getting sick. Okay? By not coming from a hot outside temperature and going into a freezing cold air-conditioned building, also the health aspect of that, okay, was a huge surprise to them. So if you look here, this building pays itself off already. So the payback period on green features is thus less than 5 years. So what I'm going to do now is I'm going to show you the engineer actually telling you about this building. It's about a 5-10 minute video, and then you can head out. It is on here, and it is also in the sustainability site.
Welcome to CH2. I'm Rob Adams, and I'm going to take you through this building. This is Australia's most advanced purpose-built commercial office building. It has two major features. It reduces its energy consumption by up to 80%, and it also provides a healthy indoor living environment for the occupants of the building. One of the simplest and most effective features of this building is the ability to, in fact, open up these windows at night. It's called a night purge. If we open those windows for 4 hours at a night during the summer, we use the cool air that flows in to cool down the concrete ceilings above me. This provides us with a saving of about 20% of the energy in the building. CH2 does not use conventional technology to cool the building. Whereas conventional buildings use air, CH2 uses water. It cools its water passively by lowering water through 15 metres on 5 shower towers on the southern facade of the building. That building is taken at 13 degrees down to the basement, where it's stored in 3 large tanks. In those large tanks we have 10,000 balls, similar to this one, that contain a phase change material. That material freezes at 15 degrees. When we need cool energy back in the building, we then pass the water back over the balls, defrosting them and bringing them into these panels here. The water then drops cool air back into the volume, making the indoor air environment the correct temperature. While we're on water, the building saves 70% of its water by mining the sewer. In the basement of the building, we have a sewer mine that draws sewerage out of the street from the drain, purifies that, and then using the water internally within the building. The water is used for cooling. It is also used for irrigation and for flushing the toilets. One of the design features of CH2 is the way we've actually utilised natural and artificial lighting. We've maximised the use of natural lighting by positioning the windows at the highest point in the vault in the roof. With artificial lighting, we've set the light at 150 lux rather than the normal 350 lux that is used in conventional buildings. But we've supplemented that with task lamps at each of the workstations so that people work within a good light environment while minimising the light and energy used within CH2. One of the most difficult aspects in designing any building is how to keep the hot afternoon sun off the western facade. What we've used is recycled louvers here that tilt in the afternoon and close down to protect that western facade. We can use a very natural way of producing a very environmental solution for the western elevation. Other aspects of the building are its passive energy systems. The solar voltaic system that is on the roof that generates solar energy, and the solar hot water system that generates the hot water for the building. In combination with the passive systems, we have systems like cogeneration, which is gas-generated electricity, a clean energy, that provides us with up to 10% of our energy. The turbines help evacuate air out of the building. They also generate a small amount of electricity which is put back into the grid. Some of the general features of CH2 are the way we've tried to replicate the leaf area on the site. Through the use of plants on the roof garden here and on the northern facade, not only do they protect the building, but they provide an equal amount of leaf area to that which had been on the site originally. The second major feature of this building is the way it has been designed to keep the indoor air environment a healthy environment for the occupants. This is the major cost saving of any building. Too often buildings have disregarded the most expensive item in the building, namely the people. CH2 operates on 100% fresh air. The fresh air is drawn down from the roof of the building, down these ducts, which look like the wall behind me, and under the floor and rise up through registers in the floor. The temperature of the air is 21 degrees, and my body and the computer heats up that air and allows it to warm and rise. As it warms and rises, it exits via the slots between the concrete ceilings here and is carried down in the belly of those, which is a duct, to the northern facade where it's evacuated out at the roof. We get 2 air changes every hour. This has been shown to contribute to about a 10.9% improvement in productivity and well-being, equal to over $2 million a year in savings to the council. 2 other aspects that provide a healthy indoor environment are the use of plants. In the building, there's 1 plant for every occupant of a floor of the building. They help clean the air and add a refinement to the air quality. It's interesting to note that in conventional buildings, these plants would need to be changed every 2 months. But the plants in CH2 have been going for 18 months and are still in a healthy condition. Another aspect are the materials we've used in the building. None of the materials have any off-gassing. They are natural and have been, in many cases, recycled from a previous life. This means that you're not getting added to the air impurities that give people headaches and make them feel uncomfortable in the working environment. the carpets are recyclable, and there's been no excessive use of paint within the building, and most of the materials have been kept natural. The question often asked is, how much does all of this cost? Well, the building cost $52 million to build, and about $11 million of that was used for the environmental and indoor air quality features. The payback period on that is quite interesting. While energy prices in Australia are still quite low and are projected to rise, they only produce about $360,000 saving a year. But the major saving comes from the indoor living environment. A recent survey done by Adrian Lehrman, a UK expert, showed that we were saving, on a productivity and well-being basis, 10.9% of our staff's time. This equates to well over $2 million. On this basis, the building will pay back all the $11 million within a period of 5 to 6 years. The economic argument is no longer an impediment for making your building environmentally friendly and the indoor air environment friendly to the people who work within it. I hope you've enjoyed your journey around the building of the future. And I think you maybe have learnt that the buildings of the future aren't that frightening. In fact, it would be a far better existence for us all. Thank you.
Okay, so when you do your Project 3 and look at Task 5, please be a little bit more inventive than water tanks and solar panels. See if you can come up with something a bit more exciting. I hope you've learned something, and I'll see you all on Wednesday ready to work hard.